This is the theorem we had last time. It's next neighbor's business. There I've got to do that. Let P and Q be distinct primes in R. Then there exists distinct primes. P1 inside Q1 such that but the key here is these are sort of next neighbors in the following sense, such that there's no prime between P1 and P1. Okay, so let's go through why that would be true. So first, extract maximal chain of primes. So the first thing that I claim, and I don't really prove in the notes, but we'll go through it here, that there's a maximal chain of primes between people, right? Goodness, how would we show such a thing? So I found. Oh, yeah, that's kind of the key for any kind of crazy gang like this, right? Certainly, it's going to be its own one. So let's look at it. So let's let gamma equal the collection of C is a chain of primes between P and Q. And I might as well say, just for convenience, if I need it, that the way the chain works is, so this is a collection of primes, and my big one is going to be Q, and my little one's going to be P. And everything else is between there, all the PIs are between there, and I can compare them all. Right? Okay. This is a set, I think we can agree. Gamma is not empty. Why? Right. There's a chain, right, between P and Q. And again, remember my chain has maximal element with Q and smallest element with P, and this is of course certainly the smallest chain that I can make. Okay. How do we want to partially order this? That might be a little bit more of a mystery. What's the appropriate partial order put on this? What's that now? Sure, that'll work actually. We make gamma a cosine by inclusion. Let me make this more precise a little bit. We'll say that C1 is contained in C2 if every element, and by element, of course, I mean prime ideal of C1 is in C2. So in other words, basically C2 is a bigger chain. It contains all the elements of the chain C1. Right? So that's the way that my partial ordering is going to work. Notice that, of course, this is a partially ordered set, right? I mean, there's no guarantee that two chains are comparable. You might have the chain PP1Q and PP2Q, and P1 and P2 are comparable, so those two wouldn't be. But this is a post set under set theoretical conclusion, right? Now, all we have to do is to apply Zorn, we need to show that any chain in this post set has an upper bound. So it's a chain of chains of primes, right? So we need to show that any chain in gamma has an upper bound. Let me call this chain something. So to that end, I think we take the approach that we almost always do. I guess the first thing we need to verify is that number one is U a chain of primes. I mean, we still need to verify that. Well, here's what I do know. I do know that U is this big, huge collection of primes. Right, because what did I do? I unioned a bunch of chain of primes, everything involved is a prime. So this is some big orgy of prime ideals, right? But I'm not quite sure if two prime ideals are comparable. That's what I have to check, right? So let's see. Let's say P alpha and P beta be in. Right. Well, what does that mean? U is a union. I love unions. So that means that P alpha and P beta both live in some one of these CIs. So P alpha is in chain I and P beta is in chain J. Right? Fantastic. And what do we know about these chains? This is a chain of chains, right? So without loss of generality, we'll say that CI is contained in CJ, right? Well, this means that, oh, Jay, you're out there. There's no obligation for this, but if you want to control the camera, just give me a holler. So what we have here is CI is contained in CJ. So CJ is a chain that's sort of finer than CI because it contains more prime ideals. So in particular, P alpha and P, they have to be in this larger chain. Right? But CJ is a chain. We have P alpha is contained in P beta, or P beta is contained in P alpha. And so, check. Our union, this union of chains of primes, is in fact itself a chain of primes. Everybody okay with it?
I will.
Yeah.
So you said that the chain CI is in the chain CJ. Can you explain again how we know that that's true?
Because the CI was a chain of primes. That means that every one of these CIs are comparable, right? So this chain of primes is a chain. So let me add some pros at the beginning of this, if that helps. Let me say this. Oh, right. I think CI. This is a chain of chains. What I'm chaining is chain. So if I pick two of these, one of these chains has to be the bigger one.
Right.
Is that clear?
Yeah.
Okay, so where are we at now? Well, I know that this big thing is a chain of prime. What else do I know? Also, for all, let's say P alpha and U, of course, all the primes fall between P and Q, because all the primes in each one of these individual chains do, and P and Q are in U, because P and Q are in every one of the chains. All right, so I'm really making sure that I've got this all right. What else do we know? We'll see. What do we know? Now we know that U is honest to goodness a chain of primes. We know that it is a chain of primes between P and Q, the bookends are both in U. Okay. And so U is an upper bound. For the chain. And because it is a chain of primes between P and Q, containing both P and Q. And of course, it's an upper bound because it's an upper bound of that chain because any one of those CIs in the chain is contained in U by definition. So we can apply Zorn's lemma. There is a maximum of primes. Yes.
So in this sense, like a maximal chain of primes means that there's like a chain of like longest length that we can kind of think of.
Right. I mean, I almost think about it like the real numbers because it could be a density thing. Yeah. What it means to be a maximal chain is you cannot jam any of the prime ideals in there. You're stuck. It is absolutely busted at the seams full, right? And of course, let me point out that this maximal chain may not be unique, right? You might start with different seeds to get different maximal chains, but you can't add any more primes to this, right? So that is to say, let me make that precise. In this maximal chain, so you get this maximal chain, if you pick any prime between P and Q, right? Any prime ideal at all, it's not necessarily in that chain, but if it's comparable to every element of the chain, then it's in the chain, right? So any prime between P and Q that's not in the chain is not comparable to at least one prime in the chain. Okay, so now what do we have? We've got this maximal chain between P and Q. And so I am going to pick first X in Q non-trivial. So I'm gonna pick X in big prime, that's not in the small prime. I can do this because I assume that P and Q are distinct. And we will let P1 be the union was, let's see the precise chain. So I'm gonna call it something, I call it C. Now selecting the X, it's in Q minus P, and I'm gonna let P1 be the union of elements in the chain that do not contain X. So I take this maximal chain, and basically what I do is I take the union of all prime ideals that I find in this chain that don't contain X. Okay. And I'm going to let Q1 be the intersection of the elements in the chain that do contain X. Notice that by a previous result, P1 and Q1 are both prime ideals. Right? Because with that previous result that said, if you union a chain of primes, you get a prime, and if you intersect a chain of primes, you get a prime. And let me also point out that we know this for sure. Certainly the fact that P1 and P2 are in between P and Q is pretty clear, right? Why is P1 contained inside of Q1, right? Well, it's because it's a chain, right? So notice all the primes here. So what you're doing is you're union all P1 is the union of all primes that don't contain X. So you grow it up as large as you can to not take X. These primes are the intersection of primes that do contain X. So given any two primes in this chain, they're comparable, right? And so you get this containment right here, right? So why is it strict? It remains to verify that P1 is strict inside of this. So assume oh, no, that's not it. It remains to verify that it doesn't get clean there. Let me point out, note one. How do I know that? That's because of X, right? Because X is in Q1, but not in P1. So there we go. And it remains to show next numbers. In that regard, we have to show that there's no prime in between there. So by way of contradiction, let's assume that there is one. Let's assume that there is a prime between P1 and Q1. Call it P. Call it fancy P. Suppose that there is a prime in between here. But ask yourself this, is X here or is it not here? Because note, if X is in P, then this contains Q1. And so we have equality. And if X is not in P, then if X is not in P, then this is part of the union. And so P is contained in P1, and we have equality. So really, I mean, that's not too difficult. The big part about that was the Zorn's-Limit part and verifying that there actually is such a thing as a maximum change. That was really kind of the engine behind it. Okay. Jake got tired of my bad correcting. Approved. Okay. Any questions?
For that part, if you want to use further in Q1, then you could take Q1 and Q12 gamma.
Not necessarily. What was gamma? Gamma was the collection of all the chains. Yes. So whatever this maximal chain is that we found via Zorn's limit, that will be one of the elements of gamma, actually. Right. But yeah, this is all part of this maximal chain, right? Because this union of primes is in the chain, and so is this intersection. Yes.
Looking at a ring that has only common many ideals, can we just say that the theorem holds for any Q1 between P and P? You can just pick an arbitrary Q1 and there will be a P1 that satisfies this.
Okay, so run that by me. So you're assuming you've got countably many ideals.
Then is it true that you have P ideals P and Q that for any ideal contained between P and Q, call it Q1, that there exists a P1 such that this theorem holds?
So let me. So if you've got P and Q, and you've got some P1, these are all prime, right?
Yeah.
And so what's the remaining part of the question?
Well, that there will be, I guess, a Q1 that is contained in P1, and there's no maximal ideal. There's no prime ideal between.
Yeah, so I'm not sure I understand the subtlety of your question yet, so maybe I'll have to cogitate, but let me give you a word of caution. I like this example here. So, when you're talking about change of primes, so let me ask you this. Let me take the real numbers, whatever you want. Take a polynomial ring over a field. Countably many variables. Right? How big can you change the primes? They can certainly be big, or you won't think, right? I mean, it's pretty easy to make a countable chain of primes, right? Notice when you line out by any ideal generated by finitely many of these variables, you get a prime ideal. Because, for example, imagine that you have the ideal generated by X1 and X3. When you mod out by that, you get a polynomial ring, and infinitely many variables, still an integral domain, right? No problem. And in fact, let me give you a chain of primes. And that's straight. And you can do like this forever. Right, and actually, in this chain right here, there aren't any ideals in between these two. There aren't any prime ideals between here. There aren't any prime ideals between here, right? So you can stack these uncountably high, right? Everybody okay with that? Can anybody give an uncountable chain? Is there an uncountable chain? Oh, good stuff. This is actually kind of weird. Which is bigger? The natural numbers or the rational numbers? They're the same, right? They're both countably infinite degrees. Let's consider this ring here. Let's index the polynomial variables by the positive rationals, right? There is a one-to-one correspondence between the number of variables here and the number of variables here. Agree? There is a bijective function from 1, 2, 3, 4, blah, 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 to the positive rationals. That bijection induces an isomorphism of rings. So this ring is the same as the other. Consider P alpha the ideal generated by the set X, well, let me call it beta. The ideal generated by X beta, where beta, or I'm sorry, let's say X alpha, where alpha is strictly less than beta. Well, beta is a real number, right? So for example, what I can do is I can have, for example, P of 1. This is generated by all the variables whose subscript is a rational number less than 1, right? But I can also do, for example, P of the square root 2. That'll be generated by every subscripted rational variable that's less than the square root of 2, which will be distinct from every other real number. If you look at P beta, as beta ranges through the positive real numbers, that is an uncountable chain of prime ideals, right? And so you should be able to do it there, right? Good luck with all that, right? But it's there, right? So this is kind of weird. See, I love it when I put that look on my graduate students' faces. Awesome. Right? But yeah, so that gives an example of an uncountable chain. And of course, I guess at the end of the day, it's not too surprising, right? Because once you have a countable number of variables, this has a huge number of ideals. Even though these are kind of the easy ideals, the ones that I have over here. But really, what are the number of subsets of a countable set? It's very large, right? It's the size of the continuum, right? And so prime ideals are actually subsets. And so, yeah. So any questions on that? So the upshot is, I think, but hey, very strange. Yes.
What was the important part of these various crimes? Was that proof that someone's limit of the preservation of big crimes in the chain, or?
Oh, well, the prime ideal, but, let's see if I understand your question correctly. Yeah, I mean, the prime ideals. Well, so the reason that we care about prime ideals in the first place is, we haven't gotten to this yet, but there is a measure of size, and I'm not answering your question, so I'm gonna ask you for a recap of your question, but the reason for discussing chains of primes is there is a way to measure the size of a ring called Kroll dimension. And it's basically how high, this is very fast, so I'll make this more precise later, but basically, how high can I stack my prime ideals, right? So in a principal ideal domain, this is what we call Kroll dimension 1, because here's how you can stack your prime ideals. 0, well, it's not a field, 0 and any non-zero prime ideal is maximal. That's Kroll dimension 1. A field, 0 is a maximal ideal prime, it's Kroll dimension 0, right? A polynomial ring over a field in 2 variables is Kroll dimension 2, because you can stack prime ideals 0, 1, 2, if you only have 2 variables, and that's how you go. This has, if one or the longest length of chains exceeds countable here, but I'm not.
Well, I'm not sure where we use the property of these being violated.
Oh, okay, yes, okay, I'm with you now. We didn't, right? So this is specifically something about prime ideals. We're just picking them out because they're important, and we're going to use these kind of concepts later, right? But of course, let me also point out that next neighbor stuff also depends on primes in the following set, in the following sense. Those 2 next neighbor primes, the P1 and Q1 that you got, there aren't any prime ideals in there, but usually one expects there to be ideals.
Okay, that's one more question.
Sure.
So I'm just thinking a little bit about the argument over there about the P equals P1 and Q1, and we get that by like set theoretic arguments because of the union intersection and stuff. But the part that I'm still not seeing is, it feels like that argument works without a maximal chain. Can you explain how maximality gave us that?
Because, for example, what I've done here is I've taken a union of a bunch of crap in the chain. I want that union to still be in the chain. But if the chain's not maximal, there's no guarantee that union of primes will still be in the chain. All right, same here. Right, I've got an intersection of prime ideals. They may intersect with something that's bigger than P, but still not be in the chain. So I need it to kind of be closed under the union. Right? So maximal chains can use this way.
Okay, thank you.
Others. Okay. Now we're going to talk a little bit about localizations, and the talk I'm going to give you is a little bit domain centric. I am a big fan of the domain case. Probably part of your next assignment, I might have to kind of patch in some details about more general localizations, and yeah, we'll see. So we talked a lot about multiplicative sets. We have a bunch of groovy theorems about them, right? I mean, you have a multiplicative set that misses an ideal, you grow that ideal to a prime. If you have a saturated multiplicatively closed set, it's the complement of a set theoretic union of prime ideals. These are big theorems. What we're going to do here is so let's think about integral domains first. But I'm assuming that a lot of you in 8510 solve this in a more general setting where you have theory classes and play itself. Have an idea. I have you guys patch this together for me. But integral domains is an important setting. This generalizes the notion of fact, quotient fields are a, special case of, localization, so. And remind you, if R is a domain, then its quotient field K, well, this is just all the fractions you can make. With a non-zero denominator, right? It's the smallest field that contains the integral domain R. So for example, the quotient field of the integers is the rational numbers. The quotient field, for those of you that are number theory junkies out there, the quotient field of the Gaussian integers is Q adjoined with I, right? Which is a field you probably saw if you saw some Galois. The quotient field of Q, X, Y, polynomials over the rational numbers in two variables, X, Y, its quotient field are rational functions in two variables, right? All possible quotients. And the idea is, I'm going to erase this quickly. I don't want the South Carolina state legislator to walk in here and think that math is all a sham because I'm teaching about the graduate students how to add fractions or something. But this is the way we add fractions, right? And so what do you need to be able to add fractions, right? Well, okay, here's what you need. You need to, let's assume that A, B, C, D are all elements of the ring, right? Well, okay, you need to be able to have sums and products, okay? Well, no problemo, right? Because we've got a ring. What else do we need? Well, one of the things that's in common to both of those little computations is if B is a denominator and D is a denominator, then I need BD to be a denominator, right? That's the big thing about the way we define addition in these localization. Denominators need to be a multiplicably closed set. And that's the importance of the multiplicably closed set there. So, definition. Of course, the quotient field for an integral domain is all fractions as long as the denominator is not zero. And actually, I'll ask you in a more general setting what happens if you allow zero denominator. And you'll see that you can do it, but it's boring as heck. The quotient field allows all fractions to make sense. That is, no zero denominators. And of course, all this is going to work because if you're in an integral domain, what are your denominators allowed to be? Non-zero elements. In an integral domain, when you multiply two non-zero elements, what do you get? A non-zero element. So you're good to go. Localizations are a generalization where it's like, hey, you know what? Maybe I don't want to kill everything, right? Fields are very boring from an ideal theoretic point of view, right? You can kill all the ideals that way except for zero. Maybe I don't want to be quite such a mass murderer of the ideals. Maybe I only want to kill some of them. And actually, that's the idea behind localization is oftentimes you get rid of a lot of the noise, focus on the ideals you need. And so here's how we generalize this. Let R be a domain and S and R a multiplicative set. And I will send 0 times S because you get something boring, and we'll see that later. We'll just assume that now. We define localization of R of S And we write it this way. R sub S. This is the set of R over S, where R is in R, S is in S. Notice that the S doesn't contain zero, we don't have to worry about there being a zero denominator. And this is a ring with R1 over S1 plus R2 over S2 is R1 S2 plus R2 S1 over S1 S2. And 2 R1 over S1 times R2 over S2 is R1 R2 over S1 S2. So now I don't have, maybe I don't have quite as many denominators, but I've got the same thing on. Yeah.
Is S saturated?
Ah, that's a great question.
Would
I
that only be-
love that question.
Would it only be if they're irreducible?
No, here's the thing. You can multiply, you can localize in any multiplicative set you want. As long as it's multiplicative close, it doesn't matter. But it might as well be saturated in the following sense. So what happens is your set of denominators will actually pick up the saturation. So I'm so glad you asked that question. Let S be in S, right? And suppose S equals T1 with T1 T2. Right? Now Grant asked, well, maybe it's not saturated, maybe you don't have the T1 in there. In the set itself, maybe you don't. But when you form the localization, you pick it up, right? Because notice that in RS, I have 1 over S, right? So I have T1 of 1 over S, which is 1 over T2. So now, sort of for free, because you can cancel, that's why you pick up the divisors. So, and that's actually, that would make actually another kind of thing that I can throw on for localization homework. If you localize at a multiplicative set, if it's not saturated, then there's a smallest saturated multiplicative close set that contains that. So suppose you have S, multiplicative close, suppose the saturation is T, then it turns that the ring R localized at S is the same thing as R localized. So you get it for free. And before I forget it, okay, so unfortunately, I'm gonna have to introduce you to some notation that's less than optional. If P is a prime ideal in R, then R, sometimes you see this low and all of a sudden you're like, what the heck is going on now? Because you've got 0 in P. This is the part unfortunate. What this means is if this is a set, if it's just a set, then the denominators come out of S, set. If this is a prime ideal, this means not in, right, yeah. But remember, here's the thing. What do you know about a prime ideal? Its set complement is a multiplicative closed saturated set, right? So that's one of the justifications for this. So for example, if you see this notation, you can generalize this to a prime, of course, but we'll just take 2. This is the set of A over B, such that B is not in the ideal generated by 2, and that is B is odd. This is a cool ring. right? It's got zero and, zero is a prime ideal, and it's got a unique maximal ideal generated by two. Right, so it's all fractions that have an odd denominator, not quite the entire quotient field, because notice in this ring, everything that is odd is a unit. Right, because you've got one over odd, so it's a unit, right? Everything that's even is not even. And everything that's even forms a maximal ideal. By the way, what is Z localized at zero? Right, it's now you're allowing your set to be everything that's not zero. This is rational numbers. Right, that's the same thing. In fact, any integral domain localized at the zero ideal is its quotient field. So let me make the following observation. Quick definition here. Unnumbered. A ring community with identity is called one quasi-local. If R, I should call it something, if R has a unique maximal ideal. One B is called local. If it is quasi-local. And here. There is some confusion sometimes in the literature. You gotta be a little bit careful. Some people use the word local just to be unique maximal ideal. But people that do more general computer algebra are more careful, I think, about this particular distinction. Quasi-local means only one maximal ideal. Local means there's only one maximal ideal and every ideal is finally generated. Right? So if you ever see the terminology local, it is very likely that they're also referring to an Euclidean ring. It is called, and I'm not kidding, semi-quasi-local if R has finitely many maximal ideals. And B, semi-local. Semi-quasi. And and let me give you kind of a quick thing. So, yeah. R is a ring community like that, and P and R is a prime ideal. Then R localized to P is actually quasi-local. And its unique maximal ideal is generated by P. We will talk more about localization and this kind of correspondence. And in fact, basically, if you have a ring and you have some prime ideals in there, under certain conditions, you can basically cherry pick those prime ideals out and form a localization. It gets rid of all the primes except the ones that you want to focus on. Okay, any questions on that? Any questions? All right, well, but there's actually no math club this weekend. Those of you that are new here, or I forget what happened during the pandemic anyway, but actually this Friday is First Friday, so they have a parade and all this kind of thing. Which means if you like parades, good for you. And if you don't like parades, you better leave before they start. Otherwise, you will be trapped here in parade hell. So anyway, you all have a good one, and we will see you on Friday.